This is the microphone, right? Okay, perfect. So I'll change the slide. Okay, cool. Thank you for having me here today. I really, really appreciate this opportunity to talk to all of you, the Bell Labs people and non. So what we generally do with those seminars, we describe a little bit of our vision, where we are going from a broader perspective, and then we tune into more a technical talk where we describe some of our recent results on one of the many projects that we are working on. So before we enter the detail of this technical talk, I just wanted to mention one program I'm driving, which is called Augmented Human Cognition. And the core idea there, or question, is how can we design intelligent algorithms and solutions that will allow us as humans to be augmented and amplified in the way we leverage our cognitive abilities. So it's a natural question to talk about artificial intelligence and define artificial intelligence, what's artificial and what's human cognition, and how we can combine those two. So some years ago we said maybe it's not artificial, we really want to augment our human capabilities, but then we thought that not that definition wasn't really the right one, and we started to ask, what's the real definition of intelligence in general? So if we think about intelligence, there are 4 key aspects that we can identify as the dimension of intelligence. Is how we perceive the world, is the stimuli that get into our brain and gives us the ability to associate meaning to that. Is how we use those information to predict what's about to happen if I'm walking or about to trip and react to that. So interpreting the world and the ideas around us and to react to those. So those we thought were interesting dimension to define intelligence. And then we also realized that, and I liked very much a discussion I had with Philippe this morning, try to define what's our brain is good at and what our algorithms are good at. And here, some of the dimension, our brain, it's not really designed to compute algorithm or complex mathematical formula, but computer can do it quite easily. So technology has been proved to be very successful there. We can't remember so many information. So our memory is limited. Computers have a very cheap memory, and we can expand to few terabytes, no problem. And data. How many data can we analyze with our brain? We go through logs, we go through information, and after very little amount of time, our cognitive ability is completely consumed. We feel the fatigue of going through those tasks. So we have designed algorithms to do those things, to complement us. And where are we today? Our algorithm can recognize cat, a person, even more. Our empathic responses, are we happy or are we sad? Yes, we can trick them, but in general, those algorithms can understand if a person is smiling or not. Predict very fast, so think about stock, trend analysis, right? Huge amount of data in real time. Interpret, in some cases, even in the medical domain, deep learning has been proved to create prediction that is better than doctor in the field to identify if there is or not a cancer or a tumor. And React, Boston Dynamics, the best in the world, they have this super agile robot. It's a little creepy. I shouldn't have said it's a man. No.
The cheetah is.
You like it? I like it. Because it does the flip. Inference. So, what am I saying? That my definition of intelligence maybe is not the right one, because otherwise it means that we have done algorithms that are better than us. So I don't think that definition was the right one. Today in Bell Labs, we are lucky enough that we can work with neuroscientists and psychologists. This is not one of them that we have in Bell Labs, but this is a leading neuroscientist. And Antonio Damasio says that we are not thinking machine that feel, but rather feeling machine that think. What does that mean? That our definition of intelligence, it most possibly needs to encompass our whole body. We have a second neural network in our gut. When we say gut feeling, it's not just a way to define intuition. It's our body sensing each other, sensing what we believe is the right step forward, and providing our brain a more extended way to think and to ingest insight and sense the information. So we really believe that the way we should think about intelligence in the future and the way we should think about augmenting human cognition and intelligence is to use those 4 dimensions, how we sense beyond our human capability, how we empathize with each other. In person, we can do very easily. Put a screen in the middle, and our ability to sense our emotional state completely drops. I was talking with our neuroscientist, and she was telling me about one experiment. When we are in person, so many parts of our brain light up. This does not happen on the same conversation if we are doing through the phone or through a screen. So our body and our brain respond in different way if we are in physical proximity or not. Interact. How can we interact beyond our human possibility? And how we can do what we do best as human, create. We can invent, we can imagine things that do not exist. Our algorithm can recognize things that we show them what those things mean. So in Bell Labs, we are working on those dimensions in different divisions, in different parts of the organization. We have extended way to sense ourselves and the space, this concept of future wearables, which will allow us as people to understand the environment and ourselves beyond what we can do today. We have projects around empathic communication, and this is the ability of having the same biological response that we have when we are in person, even when we are not in person. How can we communicate the non-verbal information through distance or through a technology means that today is internet or a phone, tomorrow can be something different that we cannot even imagine today. What's the next of exploring data and understanding things around us? The team here, some other people in other parts of the organization have worked on this concept of understanding a very large amount of data through similarity and ranking that provides you the ability to focus your attention on critical point and do as we do with our brain, understand things by similarity. But we want to move these towards a future where we can interact with each other and with the space through augmented information that just arrived to us at the right point in time. So create new possibility with all those new information that we will be able to understand without consuming our cognitive capacity. Today, you put a person in a VR environment, after 2 hours, even the best soldier in the world is not able to perform those easy combat strategy that is usually able to do because the world around him is overwhelming his cognitive ability. So it's understanding the trade-off between triggering people with information that stimulates your brain and consuming your cognitive power where you regress into a state and not even your average. You cannot even reach your average. So the idea is to combine what we can do as individual, what we can have machine that will support us in interconnecting our capabilities that we will create, and doing in a collective sense. I like Link, I like Bell Labs Friends, places where people can interact in natural ways, where people with different skill can collaborate and create a level of intelligence that no one of us alone can reach. There are studies from MIT. There is a beautiful book on superintelligence, it's called, where they have done many, many studies in assessing the quality of creativity and complex problem solving the group of people can achieve because they work well together. So it's the ability to create a world where machine can be part of that collective thinking that will move us to a next evolutionary phase. So really what I'm trying to say is that what we should aim for is this AI-human cognitive symbiosis. So how we can mingle and mix in our different capabilities in a way that is healthy for us as human to outperform our natural abilities. Why are we doing that? Because the world is going to become hyper-connected and complex, and we don't want to be part of passive, consuming in a passive way the opportunity of this connected world. We want to be the brain and the driver of this connectivity and this possibility to interact with each other in new ways where we dominate the technology. So understanding the limit of human and the limit of technology and how you mix them, it will get us to a place where it's particularly interesting. So what do we do about that? So this is the place where I start to go a little bit more into our technical capabilities. And in particular, all those beautiful things that I said are only possible if we evolve as human and we are able to exchange information in an effective way. I can learn much faster than what I do today. Today, I'm overwhelmed. I am overwhelmed. I'm telling you, I am. Too many emails, phone call, text messages. It's a little bit too much for my limited cognitive capacity. So how can we design things that take into account my specific psychological state, my neuroscience capacity, and adjust the information that is sent to me to match what's available? It's like having a pipe and trying to push an amount of water that is double the capacity of your pipe. It's just about to congest the pipe. It's not going to improve the throughput through that pipe, right? So natural language process, it's a natural place for us to start because it's the way we have learned to exchange information, but are we using effectively? And is technology at the point that can complement our deficiencies? So one of the problems today, we can do embedding. I'll talk about some of the latest natural language processing capabilities that we can achieve. But still, the semantic understanding and reasoning that we do and we are used to do when we communicate, machines are not quite there yet. And most importantly, machine can only do what we have taught them to do. What if we take this fantastic trained algorithm in one domain and we move on another domain? We can switch, no problem. Machine don't know what to say. One of the fundamental semantic understanding supporting structure, data structure, are taxonomies, so knowledge hierarchies. So knowledge hierarchies are those concepts where you have some general concept that are the parents, are more specific one, and then you grow this taxonomy. It's not a clean tree. It's usually a DAG, but it has this concept of parent and children in the relationship of generality. So how do we grow taxonomy in domains where we don't know a lot about? So if the taxonomy usually are manually designed, what can we do it automatically? That was the fundamental question. So can we do it in an efficient way and ingest new concept in the appropriate places of this taxonomy, independent from manual labeling. So we don't want a person doing the taxonomy. We have, even in our company, people that do domain-specific taxonomies. We want to avoid that in the future. So very practical application, even within our own industry. And also, we want a flexible and general solution that can be applied to many different ideas. So what we wanted to do, we take a corpus of text. First of all, we need to extract the new concept. We need to understand that this is a new language, and then to find a way to put these new words and new concept into the taxonomy so that you can grow it. So what do we do? The first step is new concept extraction. This sub-problem, by definition, can be a whole project. So for us, it was just a simple way through name entity recognition to detect new concept. We have empirically demonstrated that if the distance in an embedded space of the new concept versus the concept that are already in the taxonomy is more than 0.5, their cosine similarity, then it's a new concept. Empirical evidence, if more formal investigation, this is a problem by itself. But this project suppose that we have a set of new concepts. This was a way to extract. There may be a better way. It doesn't matter. Once you have the new concept, how do you inject into the taxonomy? So the fundamental unique idea was that we used semantic measure and graph-based measure to understand which are the right parents in the taxonomy and link those new ones into those. One other innovative idea that we had a concept embedding, which is a combination of doc2vec vector and the TF weighted of word2vec. And by having this vector representation, which is the combination of those two vectors, we could demonstrate a much better accuracy in our result. So what we had to do, given a set of new concepts, identify which are the possible candidates to be the parents of this one. So the first step, we do embedding of new concept and the old concept in the same embedded space, which is this combination of doc2vec and TF-weighted word2vec. And we take near neighbors around this new concept. So by just computing the distance of those vectors, I say which are the k neighbors around this point. And I take them as a possible starting point candidates. We know that in vector embedding representation, two things that are close are semantically related. But you can also have other elements which are distant in terms of semantic. So only closeness doesn't provide you an ability to say all the things that are close here are definitely related. If they are distant, for sure they are not related. But if they are close, they can be either. Okay? So we start with a collection, and now we need to take the good one and find a parent that makes sense for all of those. So we use, in order to identify the right parents, a learning to rank approach with 6 features. We studied many more, but only 6 were the final good features that we selected. 3 topological free features and 3 semantic features. So let me go quickly into both. So the first one is information propagation. So what we do, we start from those k-neighbors, and we identify those k-neighbors in the taxonomy, which is a DAG. Now we run information propagation, so we want to understand how we can reach to a node that has many of those possible starting points in common, but is not too far. For example, if I'm adding a new algorithm in the graph theory space, obviously, if you go up to computer science, it will cover all the neighbors. But it's very a general concept. You may want to identify a neighbor that is closer to this new algorithm that you want to embed into this taxonomy. So every time we go one layer up, we have a decay discount. So we want to identify a node that is high enough to have a good coverage, but not too high to be too general and little meaningful. So this is the first feature. Then we have 2 other ones. Random walk between a centrality. It's not a standard metric, it's a focused approach. Is starting from a set of nodes. If I run shortest path, random walk, how many shortest paths go through a possible parent. So we count all those shortest paths that go through different nodes, and we take the maximum one. And card similarity, we compute the path between 2 possible nodes. If this should be the parent of this set of possible nodes, then they should have a lot of things in common. So they should have many common random paths between them. So those were the top 3 features from a topological graph perspective. And then we have 3 features from a semantic perspective. So we compute semantic similarity between the possible parents and the node and the new concept that we are trying to put in this taxonomy. So ancestor similarity is the similarity between the new concept and the parents. The sibling similarity, me and my sister should have some similar features if we are really the 2 daughters of this same mother, right? So it's the similarity among the siblings that will define how much this possible parent is the good one for those 2 elements. And then pairwise mutual information, the usual things. Those were the top 3 semantic features that were used in our learning to rank approach. So, how did we test and train? 2 main data sets, Wikipedia and WorldNet. On Wikipedia, we use 6,000 new concepts. So we took the Wikipedia concept, we took away 6,000, we use everything else for training, and then we try to re-put back those 6,000 elements that we didn't use in the training phase. So 75% of those were identified as topic that we could reingest because they were identified from our algorithm as new concept. Among those 75, 70% of those concept-parent relation were precisely matched. And another 17% were matched with plus or minus 2. Okay? So 2 parents too high, 2 parents too low. Okay? respect to what's today in Wikipedia that we used as the ground truth. In WorldNet, we train on 400 concepts, and we test on 600 new concepts. And we compared with some baseline approach, state of art in literature. We use different metrics. Lambda match is at least one word is a predicted synset common between the current set of words that define a concept. And then a few other metrics, accuracy, recall, and harmonic distance of accuracy and recall. And our model does quite well on all those metrics. But in order to give you a practical view of what's really doing, let me give you a concrete example. This was one of the problems that we had, an earthquake in Chile in 2015. So those were the parents in Wikipedia. So those were the exact match that we had with those one in Wikipedia. So those are the one identified from our algorithm. This is a new one, but even this new concept, the earthquake in Chile, it's quite a good match. That it wasn't in the original taxonomy, but it wasn't a bad guess. This other column is Wikipedia has changes. So sometimes things get modified, and some of the category at some point were eliminated. But we have track of multiple ones, so we could see what it was done from early users. So overall, we have presented, and this paper was published in CIGIR last year, 2018. So the paper is available for everyone that wants to read a little bit more on the detail. But the idea of this work is natural language processing still misses the ability of understanding new domains, attaching more the semantic information that we attach to words and to the things that we say to each other as humans do. So we still need to push the boundary of those technology in order to help us to get to this augmented human cognition that we see as the future of our species. And with this, I really want to stop, take a few questions, and then we have another bit of a session for later. Okay? Thank you. After lunch asking question, it's a tragedy, I know. But Marco.
Actually, the talk was quite clear, so I have no question.
Very good, very good. That's a good compliment. I like it. Okay, I think we can close and maybe move more on the informal Q&A part. Okay, thank you.